Hello, my name's Clinton, and I'll be your guide through this final module of Day 9. We're going to talk about simple harmonic motion. Please don't forget to pause this presentation at any time if you need a bit more time to think about something. Last time, we saw how differential equations can be applied to study real-world phenomena. We're going to continue this study now by looking at a very basic type of motion of particles, called simple harmonic motion. Suppose we have some particle whose motion is restricted to a straight line, and denote by x of t the displacement of the particle from the origin O at time t. We will have our displacement be positive if the particle is to the right of O, and negative if it's to the left, to fit in with our usual choice of signs. The velocity of the particle is given by the derivative v equals dx dt. And the acceleration is given by its derivative, that is, the second derivative, a equals dv dt equals d squared x dt squared. Simple harmonic motion is a special example of this type of scenario, wherein a particle moves back and forth along a straight line in such a way that its acceleration is always directed towards the origin and is always proportional to its displacement from the origin. This horrible sounding sentence gives a wonderful example of how concise mathematical notation can be. If x is less than 0, the acceleration will be positive, because we want it to be towards the origin, and if x is greater than 0, the acceleration will be negative, for the same reason. Since we need the acceleration to be proportional to the displacement, we need the equation to look like this: d squared x dt squared, which is the acceleration, to be equal to minus k times x for some positive constant k. You should check that this agrees with the information on the previous slide. You will usually see this written as d squared x dt squared equals negative n squared x for some constant n. We'll see why shortly, but this is fine, since we can just replace k by n squared above, where n is the square root of k. It turns out that a solution to this differential equation is x equals a sine nt plus alpha, where a and alpha are both arbitrary constants. Let's check this. Differentiating once gives dx dt is n times a cos nt plus alpha, using the chain rule and remembering that the derivative of sine is cos. And differentiating again, remembering the derivative of cos is negative sine, gives d squared x dt squared is minus n squared a sine nt plus alpha, which is just minus n squared times our original function x. The path followed by such a particle gives an oscillation between x equals a and x equals minus a, which is the amplitude of the graph x equals a sine nt plus alpha. The particle will complete a full period, that is, moving all the way from the origin to a, then back down to minus a, and then back to the origin, in time t equals 2 pi on n, which is of course the period of the graph x equals a sine nt plus alpha. This is where these words come from. The graph of displacement x versus time t will therefore look like this, just the graph of the function x equals a sine nt plus alpha. At every point, t, the x value gives the displacement of the particle from the origin. Let's have a look at an example. Suppose the equation governing the motion of a particle along a straight line, which is an example of simple harmonic motion as we've just seen, with n equals 4, is d squared x dt squared is minus 16x. Additionally, we are given the following initial conditions. At time 0, the particle is at the origin, that is x equals 0, and also at time 0, the particle is moving to the right with velocity 2. Let's find a formula for the displacement x at any time t. We know that n equals 4, and so by our discussion above, the formula for displacement x at a given time t is x of t is a sine 4t plus alpha, for some constants a and alpha which we must determine. In order to determine these constants, we need to use the rest of the information given to us in the question. Remember that the particle was at the origin at time 0, so plugging t equals 0 into the formula means a sine alpha must be 0. Since a is non-zero, otherwise our function would be pretty boring, this means sine alpha is 0, so alpha must be 0. Or some integer multiple of pi, but let's take 0 for simplicity's sake. So now we know alpha. To find a, let's use our next piece of information, that the velocity at time 0 is 2. This means dx dt, which is 4a cos 4t plus alpha, is equal to 2 when we plug in 0. Remembering we also know alpha is 0, this gives 2 equals 4a, so a must be a half. So a is a half and alpha is 0, which means our equation is x of t is a half sine 4t. If we want to sketch this curve, remember its amplitude is a half, and its period is 2 pi on 4, which is pi on 2. Have a go at these practice questions, which will give you some familiarity with simple harmonic motion. Press pause, and then press play when you're ready to continue. Here are the answers.